Did you know that a material that looks like it could break with the slightest bend?
Actually carries nearly 99% of all international internet traffic across the oceans. To transform this fragile
material into submarine cables capable of surviving decades on the ocean floor, factories must process raw glass
through high-temperature drawing towers, precision fiber pulling systems.
The entire process is controlled with micrometer-level precision. Even a microscopic crack rejected. Join Factron process as we dive deep into the fiber-optic cable production line and discover how the telecommunications industry builds the global network. Fiber-optic cables have become the nervous system of the digital world. Running through cities and stretching deep beneath the oceans are more than 1.5 million kilometers.
Connecting data centers, banks, mobile networks. The undersea network alone includes more than 600 active or planned.
The rapid expansion of cloud computing and artificial intelligence is pushing demand,
turning the technological race into something no longer controlled solely by. Meta has signed an agreement worth up to $6 billion with Corning
for its data centers. The global fiber optic market could reach nearly 18 billion.
Behind this massive wave of investment lies a simple reality.
Depends on these tiny strands of glass transmitting light at almost instantaneous speeds. Beneath its seemingly simple plastic jacket lies a multi-layered structure, ultra-pure glass core, where data signals travel in the form of light. Think thin as a human hair. Surrounding it is the cladding, which has a slightly lower refractive index. It helps keep the light confined within the fiber instead of allowing it to escape. Placed inside buffer tubes containing gel or water-blocking material.
Aramid yarn, steel wire, or metallic armor may be added before the entire structure is sealed.
The journey of optical fiber begins in vast quartz sand deposits. Stones and gravel are retained by screening equipment, while soil, fine dust, and unwanted mineral
receive around 200 tons of raw sand every hour. However, only about 100 tons of silica sand,
foundry sand, concrete sand, or road-based material instead of being discarded entirely. Must first be converted into silicon compounds and then purified inside sealed processing systems.
To remove nearly all iron, moisture, and other remaining contaminants.
Special glass that allows light to travel for tens of miles without weakening too quickly. From ultra-clean silica feedstock, the factory begins creating the most critical component.
Ultra-pure silicon material is inserted into a hollow silica tube about 3 to 6 feet long, which is rotating on a lathe.
Flame hotter than 3,600 degrees Fahrenheit continuously sweeps along the tube's surface.
Deposits an extremely thin layer of silica on the inner wall. So thin it is almost invisible.
These microscopic layers gradually build up, transforming the hollow interior into an increasingly solid glass.
Composition of the gas flow is also adjusted throughout. The outer layers are engineered to guide and point-tuned to become the signal-carrying core. once the structure reaches sufficient thickness. The white silica layers to gradually turn transparent and the central hollow space to shrink until it disappears. At the end of the process, the original glass tube has become a solid preform rod several centimeters thick.
The path of light has already been precisely engineered inside it.
The preform already contains the light-transmitting core, suspended at the top of a drawing tower and slowly lowered into nearly 3,600 degrees Fahrenheit. The lower end gradually softens and stretches into a drop of molten glass. Grip the tip and accelerate until the large glass rod is reduced to a thread just 125 micrometers wide,
Thinner than a human hair. From this point, the preform steadily becomes shorter at the top.
The faster the drawing speed, the more difficult it becomes to keep the fiber uniform. So laser sensors continuously measure its diameter.
The pulling wheels immediately speed up. If it becomes too thin, the system slows down at once.
A historic breakthrough occurred at this very stage in 1970. Scientists at Corning successfully drew a fiber, but the telecommunications industry considered necessary for practical use. That achievement helped open the way for the extraordinary development.
The optical fibers newly drawn from the preform immediately enter a rigorous inspection line,
where even the smallest deviations and cracks must be detected. The fiber runs continuously through the system, while cameras and sensors monitor its diameter, roundness, and coating uniformity along its entire length. Every irregularity is recorded before
the most demanding stage, the proof test, a strength test performed across the full length of the fiber. The fiber is placed under controlled tension at 100 kpsi, comparable to suspending a brick weighing about 2 pounds from a glass strand only.
Sections that meet the standard continue through the production line, while any point containing a microscopic
crack breaks immediately and is removed before it can be buried deep inside the cable structure. After passing the inspection tests,
The transparent optical fibers still look almost identical to the naked eye. For that reason, each fiber must be given its own distinct
identity. The fiber reels are mounted on a feeding rack and guided one by one through a coloring head. An extremely thin layer of ink is applied around each fiber and immediately cure using ultraviolet light. The coating is so thin that it barely changes the fiber's diameter, yet it is durable enough to withstand bundling, cable pulling, and installation. The fiber optic industry commonly uses 12 standard colors, allowing technicians to identify each transmission path accurately during splicing or repair. The differently colored fibers then converge on the same production line. They may be arranged into a ribbon containing 12 parallel fibers or placed inside a small plastic tube from individual transmission paths. The factory begins forming organized fiber groups ready to be assembled into a larger cable. Excessive pulling force waters the glass inside. For that reason, the production line begins constructing a complete protective structure around them. The reels of fiber tubes are positioned around a stranding machine, while a central strength member runs straight through the middle. As the machine rotates, each group of fibers is laid around the core in a uniform helical pattern.
It's in the correct position, but also helps isolate the optical fibers from tensile stress, vibration, and temperature changes during installation,
locking the fibers rigidly in place. As the cable gradually takes shape, water-blocking gel or swellable tape is inserted into the cinches. Depending on the cable design, the factory may also add aramid yarn, fiberglass reinforced plastic rods, or steel wires, allowing 1,000 pounds. The entire cable core then enters an industrial extrusion unit. Molten polymer is forced under high pressure around the complete
outer jacket. The cable then passes through a cooling trough several dozen feet long, where the jacket hardens almost immediately. Remarkably,
stexuals can fit inside a cable only about 0.9 inches wide. The cables emerging from the extrusion line are still not ready for the fragile glass structure inside. Both ends of the cable are secured to a testing machine and subjected to gradually increasing tension. Standard outdoor cables must typically withstand pulling forces of around 300 to 600 pounds, while specially reinforced designs can endure short-term loads exceeding 1,000 pounds. And compressed by a series of machines, it may be exposed to transverse crushing forces of 225 to 450 pounds concentrated over a very small area. While the outer jacket repeatedly deforms, laser light continues to travel through the fibers inside, allowing the system to detect any immediate loss of signal.
Tame. Next, one end of the cable is placed beneath a 3-foot water column for 24 hours to test whether moisture can penetrate into
The required mechanical limits, maintain complete water resistance, and preserve their optical transmission quality are approved to leave the factory. These are sent to the final stage inside the factory, winding onto drums and preparation for shipment. Here, automated machinery carefully heat onto heavy-duty wooden or steel drums. To prepare for the long journey ahead, both cable ends are immediately sealed against moisture and securely fastened, while labels clearly display all technical specifications. During truck transport, the drums are chocked, locked in place with chains, and spaced apart to prevent impact. This level of care remains essential until the cable reaches the installation site, because a single heavy collision can shatter the light-transmitting core inside.
Engines and turn an entire reel into scrap, even when the outer jacket appears completely undamaged. Land-based fiber optic cables
An entire country. But for the internet to cross oceans and keep continents operating as a single network, the world relies on submarine fiber optic cables stretching more than 5,000 miles across the seafloor. Dozens of steel wire reels rotate simultaneously, wrapping each strand tightly around the core to form a continuous protective
armor. Cable sections installed near the shore are usually reinforced with thicker layers to withstand ship anchors and fishing nets.
The vessel travels ahead to measure the depth, slope, and terrain of the seabed, allowing engineers to determine the safest possible route. The cable is then arranged in large coils, inside storage tanks aboard the cable-laying ship, in the exact order in which it will be deployed. At the landing point, one end of the cable is floated from the ship toward the shore using buoys. Workers guide it through an underground conduit to the landing station, then remove the buoys so the cable can gradually sink into position. As the ship moves offshore, the cable passes through a system of guide wheels at the stern.
And the amount of cable released to maintain the correct level of slack. An underwater plow is towed behind the vessel, cutting a trench and burying the cable roughly
6 feet beneath the seabed. In deep ocean areas reaching more than 20,000 feet, heavy armor is no longer necessary. Placing a cable beneath the ocean leaves no room for error. Excessive tension can cause it to snap during deployment, while releasing too much cable can make it form loops or drift away for the surveyed route. One notable incident occurred in 2008 when several submarine cables in the Mediterranean
were severed within a short period, causing internet traffic in Egypt to fall by roughly 70%. Telephone phone service
operations across multiple countries were immediately thrown into disruption. Even a minor deviation on the ocean floor can trigger a failure that cuts off
an entire region from the global network.
Analyzing structural integrity at sector gamma, processing environmental data, synchronizing crane movements with the central nexus.
Easy now, watch the corner. A little more to the left. All right, it's locked in. Hook is secured. Ready for tension. All clear on my side. Take it up. Copy that. Lifting the load.